We've now learned enough about DNA to understand what mutations are. A mutation is basically a mistake in the process of copying DNA. There are two types of mistakes that can be made in the process of separating and then bringing in nucleotides. One possible mistake is to bring in the wrong nucleotide. In this first instance, we have on the upper strand a thymine that was brought in to connect with a guanine rather than a cytosine. So you can see on the lower strand that the proper connection has been made. It's a G that should have come, or C that should have come in with that G rather than the T. This is called a point mutation. It's when one nucleotide that should have been brought in is actually replaced with another. One nucleotide is mismatched. Now, under this circumstance, the codon that particular nucleotide would have been a part of is going to be changed. So in the representation we have here, the first letter, the first nucleotide of the codon is not a C, as it should be in the bottom strand, but in fact it's a T. That means it's going to code for a different amino acid in the protein, and it's going to change the protein. Now, sometimes that's going to affect the whole protein to just replace one amino acid. Sometimes that is deleterious and dangerous and, in fact, deadly. Sickle cell anemia, for example, is due to a point mutation. Just one nucleotide is changed. As a consequence, it has deadly effects on people. In most cases, though, a point mutation does relatively little damage to the final result. Another type of mutation is called a frame shift mutation. This is where a nucleotide is skipped or inserted. In this case, represented here, we have a situation where the cytosine was not put in, and so we're missing a nucleotide. And in this case, it creates a very big difference in the result. Because now, with a missing nucleotide, something similar with an additional nucleotide, the codon is now starting, rather than the C, it's starting with the next A. And comparing it with the proper sequence, which is shown on the bottom of the screen, we've got each codon is now different from then on. So this is why we call it a frame shift mutation. It actually shifts over the reading frame and changes every single code from there on out, every single codon, which means it'll change every single amino acid in a protein and make the protein completely useless. So a frame shift mutation is a very serious change in a protein sequence. It usually is completely destructive of the protein, and many times it will in fact kill the organism. With these two types of mutations, we have a possibility in our world of some serious problems, but fortunately, mutations are really rare. As a matter of fact, roughly at a particular location, a particular nucleotide, the chance that a frame shift or a point mutation would occur there is 1 in a million, which means we'd copy it 1,000,000 times. We'd copy the DNA 1,000,000 times before we'd expect to find even one example of a mutation at that particular site. And this is because partly because the DNA is so easy to copy. It's got such a simple set of rules that for the most part, you're going to get a proper copy every time. But it's also due to the fact that we have discovered in organisms that there's mechanisms in place that actually check the DNA, kind of like fact-checking or checking to make sure that things are in place. There's another molecule that runs along behind the molecule that's putting the T's and the A's and the C's and the G's in place and make sure that A's are going with T's, C's are going with G's. And we've got evidence there may even be a second and a third molecule that comes along and checks it a second time and a third time. And if it finds something, it changes it, puts it where it ought to be. This process of the simplicity of copying plus the checking allows for very faithful reproductions, very faithful copying. In fact, when you can make only one mistake in 1,000,000 copies, that's an amazingly good copy. When humans copy things, like at one time scribes were used to copy the Bible, they were very commonly making mistakes. They're trying to copy each letter exactly the way it should be, but it was easy for them to make a frame shift mutation, if you wish, to go from the E of one word or the ET of one word to the ET of another word and skip words in between. It could be that they make a mistake and put an A rather than an E. Of course, it's in Hebrew, so it's a different kind of, different actual letters. But the idea is that the humans make a lot more mistakes than DNA makes in its copying, fortunately, because otherwise we'd all be dead. But the amazing design of the system actually makes it possible to create extremely faithful reproductions of the original information. Now, it turns out that mutations can be induced, meaning we can actually increase the likelihood of mutations or actually cause mutations to occur or at least become more common. Radioactivity does this. It's part of the danger of radioactivity. Radioactive decay produces particles that fly through objects, including humans or animals, and in the process can actually make it very likely that either in the process of copying the DNA that the wrong thing is put in, or it will kick out things that should be there or change them into a form that it shouldn't be. X-rays do the same thing or do something similar. It's the reason why when you're going in to have your X-rays done that they put lead over areas that don't have to be X-rayed, because the X-rays can in fact induce mutations in other areas of the body. And it's why also the X-ray technician goes behind a lead wall or actually wears lead clothing themselves in order to keep the mutations from occurring in their own body. UV light does this as well. If you lay out in the sun and get a suntan or a sunburn, mutations actually are induced in the skin cells of your body. And this can result later in life in cancer. In fact, backing up to the radioactivity issue, radioactivity can cause mutations which later can develop into cancer. We saw that in the case of Nagasaki and Hiroshima, where the atom bomb was dropped on those particular cities, and people years later would in fact would actually form cancer in various cells of the body because of the radioactivity. At the dropping of the bomb, it produced mutations that ultimately led to cancer. Likewise, those who young in their life, early in their life, let's say go to a tanning salon, which uses UV light to tan you, or they lay out on the beach, lay out in the sun, and allow themselves to get burnt or tanned, very often mutations occur in their skin, and years later, that can actually develop into skin cancer. We've also got LSD, marijuana, several of the hallucinogenic drugs can actually induce mutations. We've seen that. Pesticides, there's a number of things that we have generated to kill organisms in the environment, fungicides, that actually induce mutations as well. These are things we should avoid contact with to make sure that we don't end up inducing cancer later in life. Switching to the main point of the chapter now, that we've learned a little bit about DNA and how DNA is extremely well designed to store information, copy information. DNA is also the central point of the evidence for what I call the language of life. DNA shows evidence of the language of life. Now, I want to be careful here not to say that DNA is the language of life. DNA is evidence that there is a language of life involved. The analogy would be, let's say, taking your textbook. That textbook has letters in it, words in it. The words aren't, those things in the textbook, those little characters in the textbook aren't technically language. Language is the English language that's used to understand those characters. It's something humans are utilizing in their brain to take those characters, translate them into ideas. The ideas and the transmission of ideas are actually the language involved. But nonetheless, the book is definitely evidence that there's some sort of language there. You could go to let's say, an archaeological site and discover something that has some funny little markings on it. The character of the markings might convince you that some sort of a language was involved in the construction of these marks. The marks themselves aren't a language, but they're evidence of a language that was used to place those marks on that material. In the case of DNA is not, it's kind of similar. DNA is not the actual language, but it's evidence that there's a language there. For example, language has characteristic of what we call hierarchical coding. You code at one level, and then you code at a higher level, and then you code at a higher level. This is characteristic of language. For example, let's take English and take the situation where we transmit English language via Morse code. Morse code is a process whereby we make dots and dashes into letters. So each letter of the English alphabet has a particular sequence of dots and dashes and gaps or pauses between to identify the letters of the alphabet. You've only got three possibilities with Morse code: a dot or a dash or a gap or a space. And with those three possible elements, you can code for the 26 letters of the English language. So you've got three elements that code at the first hierarchical level for 26 letters. The 26 letters themselves can be arranged in particular sequences to code for words. There's something in the order of 400,000 words in the English language. So we've got just 26 letters that can actually code for 400,000 words. The 400,000 words can be, that's the second level of coding, the words can be put together in sequences to produce sentences, concepts, very complex concepts. So we have multiple layers or hierarchical levels of coding. 3 coding for 26, 26 coding for 400,000, 400,000 coding for virtually infinite number of concepts. DNA is analogous to that. There's only 4 nucleotides that you have to choose from with DNA, but the 4 nucleotides can code for 20 amino acids. The 20 amino acids can code for something in excess of 120,000 proteins in at least the human body. So this very similar hierarchical coding, for English it's 3 to 26 to 400,000. For DNA it's 4 to 20 to 120,000. Very similar coding, suggesting maybe DNA is actually part of a language, just like Morse code would be part of a language. A second characteristic of language that seems to be found in DNA is what we call a random character order with a higher level meaning. If you were to throw, let's say, a sentence into a computer and ask it, okay, when you see a particular letter, English letter, like an A or a B or a C or a D, ask the computer whether it can predict the next letter. How predictable is the next letter in a sequence of letters in a book? Let's take the book, your own textbook. You look through the whole textbook, use all that data. If you find an E, what's the likelihood that you can correctly predict the next letter? If you find a Z, what's the likelihood you can correctly predict the next letter? What you're going to find is you can't. It appears that just having a particular letter does not allow you to predict the next character. It looks as if the characters at that level of consideration are in there randomly. That once you get an A, it seems to be a random pick from all the possible characters what the next one's going to be. As far as a computer is concerned, as far as an algorithm that we might develop to try to discover such a pattern, it seems that language has a random pattern at that lowest level. On the other hand, we know good and well that the sequence of letters in the book passes on information. It is not random. It's carrying information. It's just not carrying it at the level that that computer program is studying. You can't predict the next letter from the previous one. In that sense, it's random, but it's clearly not random. It's carrying information. Language has that characteristic. If you look at individual letters, you can't predict the next one. It appears to be random. But language carries information apparently at a higher level. Well, DNA is the same way. If you put DNA sequence, the sequence of nucleotides into DNA, or even the sequence of just the codons, you cannot predict the next nucleotide or the next codon. DNA seems to have a random character in the sense that at that scale, you can't predict the next item. Yet, we know good and well that DNA contains information, contains information on the sequence of amino acids necessary to build a protein, the recipe for a protein. Thus, DNA is not random at one scale, but at a lower scale, it is random. That's the same characteristic of language. A third characteristic of language, at least human language, are linguistic rules. We have words in the English language, and then we classify the words into categories. We have verbs and nouns and adjectives and adverbs. You have different kinds of words. And then there are linguistic rules that tell us how we should combine the words into a, for example, sentence. So we need a noun, we need a verb, got to have at least those two. And the rules in English tell us what order they should be in. And if you're going to modify the noun, you throw in an adjective, and there are rules on whether you put it in front of or after the noun. And then if you want to modify the verb, you've got to throw in an adverb, and there are rules on whether you put it before or after the verb. And then if you want further information, you add a prepositional phrase. A prepositional phrase has got to begin with a preposition, that type of word. It's got to have an object of a preposition, and then it could have, and so on and so on and so forth. There are rules about how you put the words together. These are called the linguistic rules. And for a given language, English versus Spanish versus Korean versus Swedish, there are different linguistic rules. They all deal with the same thing. They all deal with whether you have nouns and verbs and so on. But they are different as to the order, how you use the words with each other. They're unique to the language. With DNA, there appears to be something very similar to linguistic rules going on with DNA. We have different segments of the DNA which seem to have different functions. There are some segments that seem more like verbs that cause the DNA to do things. There are other sections that seem to be more like nouns. There are other sections that seem to be like adverbs telling this particular action that seems to be a verb. Another section of the DNA tells it to do it fast. Another section tells it to do it slowly, kind of like an adverb. And then there's a particular order. We have genes or segments of DNA that must be read in a particular order, as if there's some sort of rule on the order of genes. We've only just begun to see this in DNA because it's very complex. We understand very little. But there appear to be something very similar to linguistic rules going on with DNA. All of these things suggest that DNA might actually be part of a language. Another thing, the last thing that seems to be similar between DNA and language is that your textbook, for example, has to be read by something. Your textbook isn't a language, and it doesn't become a language really until something reads the textbook, takes the abstract symbols and translates them into what they symbolize, and then processes it. A language takes the evidence of language and puts it into a larger system to understand it. DNA has that same characteristic. DNA sitting by itself, sitting out on the table, can't do a thing. It doesn't do anything. It doesn't carry information. It doesn't mean anything. It only means something when you have it inside a cell, and the cell actually can take the information and use it. Outside the cell, the information is useless. It means nothing. DNA only means something in the context of a complex system. In fact, some of the things that the cell does with DNA, it's interesting how humans have given names to those processes that sound an awful lot like things people do with language. For example, the process of copying the DNA that we've talked about. You separate the strands, you bring in the proper nucleotides and so on. That process is called transcription. The transcription is a word that comes from language studies among humans. To transcribe something means you copy language from one to another. To a transcriber or a scribe is a person that copies language. It's fascinating that the process of copying DNA is given a description or a title that has to do with, its meaning really has to do with copying language. The process of taking a copy made on DNA, taking it out into the cell and making a protein from it is called translation, where we translate the information from DNA into the information on a protein. Again, translation is a term having to do with language. There's several things. These things all seem to indicate that DNA really is central to a language that's going on in the cell. This is what I call the language of life. So we have evidence in organisms, across the board, in all organisms, that there is a language of life involved in biology. So where does all this come from? Where does DNA come from? What's the origin of this? If naturalism is true, the myth of DNA that I started out by saying wasn't true should be true. If naturalism is true, then there is no creator. There is nobody who put the language of life into life. That in fact, DNA is somehow the natural result of spontaneous generation, spontaneous activity. No intelligence went into it. If that's the case, then the complexity of DNA ought to be understandable by breaking it down into its components. And in fact, organisms ought to be understandable by breaking them into successively smaller pieces. If you understood the pieces, you should understand the organism. And the piece of the organism that is most basic and different from every other organism is its DNA. So if you could understand the DNA and you believe in reductionism, in naturalism, it ought to be that you understand the whole organism. There's no emergent properties that in fact the organism has that can't be found in the DNA. Somehow the DNA should contain all the information necessary to build the organism. But in fact, that is not true. The myth of DNA is a myth. It isn't true that all the information for building an organism is found in the DNA. Therefore, reductionism is false. Therefore, naturalism is in fact false. DNA structure also seems to be extremely well designed. It's amazingly well designed. It's optimal. You can't make the DNA structure any simpler to do the things that it does. It seems to be designed by a designer that's even more complicated or more sophisticated than humans. It's consistent with the idea of the God of the Bible, the God of communication, creating DNA. Naturalism doesn't have any mechanism that can explain the origin of something like that. Also, communication in general is irreducibly complex. You can't have language unless you not only have something like DNA carrying information, but also complicated systems to read it. You can't have language unless you have a conveyor of information, a receiver of information, and some mechanism to convey information, and a whole bunch of other things that are necessary in that process. If you break down the DNA structure to its simplest structure, it's still got a bunch of pieces. It's got too many pieces to be assembled in a step-by-step, one step at a time process that's required in evolution. You have to put communication together by putting a whole bunch of pieces together at the same time. Then it works, but you can't do it in a stepwise process like evolution. So the language of life is many times more complex than anything known to be generated naturally. DNA seems to have been the product of intelligent design, of design by a God far more intelligent than we are. Which brings us to our responsibility as priests. What do we do with this information? First of all, we have a responsibility to know God. We can see evidence, we can see the character of a communicating God in the language of life, in human and animal communication, in human communication. This gives us insight into the nature of God. The fact that there's a spectrum of perfection of animal communication and human communication suggests that there is a communicator who is a perfect communicator, the God who communicates. The language of life suggests that there is a designer who has language. In fact, it suggests that biology is created by something with language. The biblical claim that in fact the Word holds everything together is consistent with the idea that there is a language of life consistent across biology. And it's also cool that the DNA that's found inside cells is very much like an ID tag that indicates made by God. Every time you see the DNA, you're convinced there's no possible way that could come about by any other way than God creating it. Therefore, when you see the DNA, you're seeing an ID tag that says made by God. And it's in every cell of every organism. It's in every one of our cells. Made by God. Made by God. The more we learn about DNA, the more we're impressed with the very nature of God Himself. We're impressed with the fact that God is creator. There's no other way that you can get this DNA except by God having created it. Naturalism doesn't have a mechanism to explain the origin of DNA. It must have been created. And the fact that He's laid all this stuff out here, simple enough for us to understand at least the major parts of it, is because God desires us to know Him. This amazing, communicating God with great intelligence and communicative power wants us to know Him. Realizing that, I can't help but actually fall into worship of Him. The more I learn about DNA, the more I learn about the language of life, the more I'm impressed with God, the more I wish to worship Him, the more I wish to bring others into worship. When I do that, I am fulfilling my responsibility as a priest of the creation. What is our responsibility as kings? Well, the main piece of information I'd like to pass on here is we know very little about DNA. We have a very small understanding of the structure of DNA. We understand a fair bit about genes that code for proteins, but that's 2% of the DNA. We understand almost nothing about the rest of the 95% of DNA. And it appears to be a language, which means it's probably carrying a lot of information that we don't have a clue about. So it'd be like, let's say you take a book that's written in a language you don't know. You don't know what this language is, you don't recognize the characters, nothing. But let's say you take that book and said, I think this book could be improved. I'm going to go in there and I'm going to change a portion of this because I think it should be made better. What's the likelihood that you, knowing nothing about this language, can make a change in that book that would actually improve that book? It's not possible. If you know so little, you can't make changes that are going to improve it. We know so little about DNA that we shouldn't be playing around with it, making changes in it. We can't randomly alter the DNA because that ends up in bad consequences. We've tried that before, and it produces mutations that are all bad. And it makes sense. If we just randomly change something in a book, it's not going to improve the book. It's probably going to make it worse. That is our observation. In general, we need to be extremely cautious about modifying DNA, cloning, genetic engineering, gene transplantation. We know so little about it at this point that these things need to be approached with great care because we're playing with a system that is far more complex than anything we have ever devised on our own. And it's very likely we're not going to be improving things, but in fact making things worse.